Hi, I want to talk about the concept of pressure. Now, if we take a look on the most microscopic level, pressure comes about because of collisions. And pressure is a property that we typically use when we're describing fluids. Since fluids are free to move around, if you try to apply a force at one point, the fluid just gets out of the way. So usually any net force that's applied needs to be applied across some area. So our definition of pressure is just equal to that net force divided by the area over which it's applied. So it comes about from collisions. As those fluid molecules collide with each other, their momentum changes. And the net force that we would see would be equal to the change in momentum of those molecules divided by the sort of sample of time with which we're using. So if we wanted to measure pressure, we could imagine what I'm going to call a magic pressure meter. So imagine that we have a spring balance that has a wall that those fluid molecules are free to collide with. So there's a spring behind it. So when a collision's happening, that spring gets pushed in just a little bit. Now, if we didn't have a lot of molecules, then we just see a little spike of force, little spike of force, little spike of force, and it would rebound. But this is impossibly small. So even if we were to take a look at something tiny, like something smaller than a fingernail, we would still be dealing with trillions of collisions even over a tiny amount of time. So what happens, because there's so many gas molecules inside normal gases, so many liquid molecules inside normal liquids, well, that pressure fluctuates, but it fluctuates a tiny amount around some stable average. And when we talk about the science of thermodynamics, we'll dive more deeply into how Newton's second law applies to that. But for now, we're just going to think of this as we can average out the amount of collisions that we have, and that's what our pressure is. The force comes about because of collisions, so our pressure is a measure of the force from those collisions over the area over which those molecules are colliding. So for units of pressure, well, in SI, force is measured in newtons, area is measured in meters squared, so the SI unit for pressure is newtons per meter squared, which we replace with the Pascal. Capital P, lowercase a, named after physicist Blaise Pascal, who did a lot of work with the science of hydraulics, another application of pressure. Now, there are a lot of units of pressure, and unfortunately, they are in use in a lot of different areas. So it's not like the case where there's a metric unit and a US customary unit. There are a ton of units that are used in different applications. So speaking of US customary units, our customary unit of force is the pound. Our A customary unit of area is square inch. So we tend to use PSI for pounds of force per square inch of area. Now, in medical fields and in especially physics where you're dealing with vacuum, high vacuum, ultra high vacuum, we often use the unit of pressure called the torr. And a change in pressure of 1 torr is equal to a change in pressure equal to the height of 1 millimeter of mercury in a standard barometer. And I'm going to do a separate discussion talking about how barometers work. Now, you would think being medicine, being physics, you would use Pascals. It's customary to use torr in a ton of areas. It just is. And torr also comes after the name of a pressure scientist named Evangelista Torricelli. Now, the other really common unit of pressure that you see in engineering is the atmosphere. Because air is colliding with us right now, we're experiencing a pressure. So the atmosphere is roughly the pressure that you'd be feeling right now if you even noticed that pressure. Now, Because it's something that can vary with the advent of standardized units, we've since defined the pressure to be an exact amount. And in pascals, 1 atmosphere is 101,325 pascals. 1.01325 times 10 to the 5 pascals. That's really close to 100,000, which would be a metric unit. So there is the metric atmosphere, which is called the bar, which is used most often in weather forecasting. If you watch a lot of the channel where they show a lot of big weather events happening, like major storms, they talk about forecasts where the pressure at the center of the storm is in centibar or millibar, 1/100th of 10 to the 5 pascals or 1,000th of 10 to the 5 pascals. So 1 bar is 101,000 pascals, so 1 atmosphere is 1.01 bar. And PSI, 14.7 pounds per square inch, is atmospheric pressure. Which brings us to our final topic. This is a magic pressure sensor, which means it doesn't work. You can't have some sort of magic sliding scale where there's nothing on one side except some sort of spring and then collisions happening on the other side. Nearly every pressure gauge that we tend to deal with is based off of relative pressure. So typically, if you're reading a pressure gauge outside of vacuum science, then the gauge that you are reading is telling you the difference in pressure from 1 atmosphere. So if you connect a tire gauge to your tire and it says 32.0 psi, it means it's 32.0 psi above 1 atmosphere of pressure. So if atmospheric pressure is 14.7 psi, inside your tire, it's actually 32 plus 14.7 or 46.7 psi. So the true pressure we call the absolute pressure. And it's typically the gauge pressure, what a differential pressure gauge would tell you, plus 1 atmosphere. So typically on a pressure gauge, it can read any value from -1 atmosphere all the way up to the dial breaking. Thanks for watching.